Okay, in the last class, we were discussing the Gaussian random variable. So the Gaussian random variable has a PDF which is given by this equation, and we have said that it is defined by two parameters, which is the mean m and the variance, that is sigma square. Okay, and the mean of this random variable is already we have discussed in the last class. It is m, and if you try to find the variance of this random variable, this comes out to be sigma square. Okay, because the variance, you can find the variance as the mean square value minus square of the mean. And if you find the mean square value of this random variable, that is integration of x square px dx, integration from minus to plus infinity. So you can put this px here, and then you can do some changes that I leave as a homework or assignment for you. Okay, so it will become basically mean square value will become 1 by sigma under root 2 pi integration of x square multiplied with this function e raised to power minus x minus m square by 2 sigma square into dx. Okay, and then you can make certain changes here, like you replace this variable x minus m over sigma with y, then definitely your x will become m plus sigma y, and this equation will be modified as 1 by sigma under root 2 pi integration of x square, which is m plus sigma y square into e to the power minus x minus m by sigma is y, so it will become e raised to the power minus y square by 2 into dx. So dx will become sigma times dy because m is a constant, so it becomes sigma dy. So this sigma and sigma gets cancelled. Then you can expand this using a plus b whole square, and you can further solve it. It comes out to be sigma square plus m square. This is the mean square value of the random variable. And if you find the variance sigma x square, which is mean square value minus square of the mean. So mean square value will be this sigma square plus m square, and mean value is m, so minus m square, so it becomes sigma square. Okay, so the Gaussian random variable is totally characterized by just two parameters. One is the mean and one is the variance of this random variable. Okay, there are so many other probability density functions that are used, but Gaussian random variable is the most important PDF that is used in the communication theory. One more PDF that you can say is uniform PDF. So uniform PDF, if I say you have a continuous random variable and it takes the x, which is the values which the random variable can take, lies between a and b, and if I say this is a continuous uniform PDF, this random variable has a uniform PDF, then the probability of x is same between a and b. And since you know that the area under the PDF has to be 1, so this value will be 1 upon b minus a, so that this area is unity. Okay, so this is what we call as the uniform PDF. Okay, it means the probability of x having a value between x and the x plus dx is basically same. Okay, so the probability of occurrence is same for all the values of the random variable. That is what is called as uniform PDF. And likewise, you can find its mean and the variance. Okay, if I suppose try to find the mean, that is integration of x into px of x dx, and this will be simply become a to b integration of x px dx, and x is 1 by b minus a, so I can take it as integration of, this is 1 by b minus a, not x, so integration of a to b x dx 1 over b minus a, because this is a constant. Okay, px dx is 1 by b minus a between a and b, so I can take this outside the integration, and this simply turns 1 by b minus a integral a to b x dx, which is 1 over b minus a integral of x is x squared by 2, and limits from a to b, so it becomes 1 by 2b minus a into b square minus a square, and that will become b minus a into b plus a, so b minus a gets cancelled, you get b plus a by 2. So this is the mean of this random variable. Of course it is the midpoint, a plus b by 2, and that should be there because the mean of the random variable is basically the center of this probability density function, right? Likewise, you can find the variance sigma x square. So sigma x square is mean square value minus square of the mean. Okay, so we already have computed this mean, which is b plus a by 2. So square of the mean will be b plus a whole square divided by 4. So what you need to find is the mean square value, and that will be integral of x square px dx, and this is again 1 by b minus a integral of x square will become x cube by 3, limits from a to b, and that is 1 by b minus a, or 1 by 3b minus a you can write, into b cube minus a cube. Okay, and this you can further simplify. It becomes 1 by 3b minus a. This I can expand as b minus a into b square plus ab plus a square. Okay, this product will generate b cube minus a cube. So this gets cancelled. You get 1 by 3 b square plus ab plus a square. This is the mean square value. And if you want to find the variance, then it is mean square value minus square of the mean. So this will become b square plus ab plus a square divided by 3 minus square of the mean, which will become b plus a whole square by 4. So it becomes b square plus a square plus 2ab divided by 4. So you can just multiply this with 4, this with 3, and then subtract. You will get it as b minus a square divided by 12. Okay, so this is the mean and the variance of the uniform PDF. Likewise, you can, if the PDF of the random variable is given to you, you can find its mean, you can find the mean square value, and subsequently you can find the variance of the random variable. Okay, now we will take an example where we use this uniform PDF. Like we have a case what we call as the quantization noise. The quantization noise in PCM. Okay, PCM stands for pulse code modulation. Pulse code modulation. It is basically a way through which the analog signals they are communicated using a digital signal. That is what is called as the pulse code modulation. Okay, so what we do in the PCM, if we have some signal, analog signal, maybe like this. Okay, this is x of t. In the analog signal, the amplitude of the signal can take any value. In fact, it has infinite number of values. Okay, but when you tend to make the signal as a digital signal, in the digital signal we have finite number of amplitudes. Okay, and if the signal just takes the two amplitude values, that is a special case, what we call as the binary signal. Okay, so if suppose we have an analog signal, and let us suppose that the maximum amplitude is MP and the minimum amplitude is minus MP. So how we convert this signal into a digital signal in the PCM? We first sample it. Okay, so sampling means that we are basically converting the continuous time signal into a discrete time signal. So we have a sampling interval here. So the signal samples now they are taken at discrete instance of time. So you take at this time maybe t naught. Then after some time, if this is t, then you take a sample at t naught plus t, then t naught plus 2t, 3. So I just store these sample values, not the continuous signal. Okay, this process is what we call as sampling. So after sampling, your signal is converted from continuous time to discrete, but it is still analog in nature. It is not digital signal. Okay, because amplitude still can take any random value, can take infinite number of values. Okay, and after sampling, if you do so in the PCM, you first sample it, which converts the continuous time signal to discrete time signal, and then that is followed by quantization. Okay, so in the quantization process, we restrict the amplitude to take certain finite values, not any random value. Okay, that is how the signal becomes a digital signal. So for that, what we do, you divide this entire amplitude axis into certain number of intervals. Okay, maybe suppose I divide this into L number of intervals. Okay, so the length of each interval, it will become definitely 2 MP divided by L, because 2 MP is the total magnitude range, and the entire magnitude range is divided into L intervals. So the width of each interval is 2 MP by L, and then you force the amplitude to take a value which lies at the center of this interval. Okay, maybe this point or this or here, here, and so on. Okay, now the amplitude cannot take any random value. These midpoints in each interval, these are only the values which the sample signal can now take. And if the sample signal amplitude does not exactly lie at the quantized levels, you have to round it to the nearest level. Okay, like suppose at this time I have this amplitude, and this amplitude suppose is here. Okay, so I will approximate this amplitude with this value, the nearest level that you have. Okay, and suppose for this time you take a sample here, and this sample exactly lies at a quantized levels. So there is no error here. Similarly, for this sample, you take it. If it exactly lies at a quantized value, then there is no error. Similarly, for this, okay, suppose this amplitude lies here, but it is actually not a permitted amplitude level. So we have to round it to the nearest level. Okay, so it means in the output you have a finite number of levels. Maybe you have L levels, L amplitude levels, or L different amplitudes. So the signal, the sample signal can take only one of these L levels. Okay, maybe 4 levels or 16 levels. So the entire amplitude range is divided into 16 different levels, and the sample signal amplitude can just take one of those levels. So that is how you convert the discrete time signal to a digital signal. Okay, but in this process you get the error what we call as the quantization error or quantization noise. Okay, because suppose, see, at this point, let me draw one more example maybe. Okay, suppose at this is my signal and these are the levels, permissible levels. Okay, and I sample it here or here or here and so on. I sample it. I have divided the amplitude into finite number of levels. Now the amplitude can either take this value or this or this. In between, no value is permitted. That is how the amplitude is restricted to take only finite set of values. Okay, and that is how it becomes digital signal. And we already said that if these are the levels, then the quantized level is the midway between this. Okay, it means any sample which is lying within this level, this interval, that will be basically quantized to this value. Similarly, any sample which is lying in this interval, it will be rounded to this point, the midpoint. So if the sample value is exactly at the midpoint, then the error is 0. But if the sample value is here, it is rounded to this point, so you get this error. This is what is called as quantization error. Okay, so the maximum quantization error that you can have, because this level, this interval, it has a width of 2 MP by L, and the maximum error that can happen is half of this. Okay, it will become MP over L. So if the sample amplitude directly lies here, then there is, suppose here, then there is no error. Okay, if it goes beyond this, in this interval, the maximum error that you can have on either side is 2 MP by L. That is, if I say M is the actual sample value and M hat is the quantized value, then M hat minus M will give you error. This is called as quantization error or quantization noise in PCM. Okay, and if you see the PDF of this noise or this error, it tends to be a uniform PDF. Okay, because if I say that the sample value can lie anywhere in the quantizing interval, then the PDF of this random variable, okay, the error signal, that this I am calling now as a random variable, okay, which is the difference between the quantized value, or you can say the actual value minus the quantized value. That difference is I am calling it as a random variable. Okay, so this x can take a minimum value of 0 when there is no error, or the maximum value of this error can be 2 MP by L. And this error since can lie anywhere between maybe minus, in fact, minus MP by L to plus MP by L. So if it is point is here, then there is 0. If it is goes below this, Then in one case you have error as positive, in one case your error is negative, this difference. Okay, if m is greater than maybe m hat, then it is a positive error, and that positive can be mp by l. And if m is less than m hat, then this error will become negative, and the negative value will be minus mp by l. So this error signal, it can take any value between mp by l and minus mp by l. So it will have a uniform PDF, mp over l to minus mp over l, and definitely this amplitude, because the area is 1, this has to be l divided by 2 mp. Okay, so that the area of this PDF is 1. So this is what I say px of x, or I can say it as p of q, pq of q. Okay, this random variable can be taken as q because it is related to the quantization noise. So I am taking a continuous time signal, I am sampling it at discrete intervals, and then I am mapping these samples to a finite set of values. Okay, and in this mapping, the difference between the actual signal value and the quantized level, that we call as a error. Okay, so that errors can lie anywhere between minus mp by l to mp by l with a uniform probability density function. So if you find the mean square value of this, you will get integral of minus mp by l to mp by l q square pq of q into dq. Okay.